Thank you. So, welcome to the talk, iPhone Exploitation, One Rope to Bind Them All. And I will skip my introduction because I have a lot of slides and I need to go through them in a way that we can finish in time. So what is this session about? This session is about the odds to successfully exploit an iPhone in case you have no kind of information leak. So you have the exploit, but you don't know what device you're exploiting. And it's not only about the odds, but it's about how to improve them. And for this talk we say we have like a normal stack buffer overflow, because otherwise we have to deal with some way to, some gadget to get the heap into, get the stack pointer into the heap. So we will just say we have a stack buffer overflow, so we just need no kind of stack pointer movement in the beginning. I want to start with some statistics. So when you look at the iDevices and the versions, you see that there are like 12 iDevice, different iDevices that are supporting iOS 4. It's the iPod 2, 3, and G, 4, I mean. And there's the iPad 1, iPad 2 Wi-Fi, iPad 2 CDMA, iPad 2 GSM. And you have the iPhones 3G, 3GS, and 4 is even available in GSM and CDMA. And of course you have the Apple TV, but I ignore it for this talk, so yeah. And the soon-to-be released iPhone 4S will most probably only support iOS 5, so we don't need to use it. We don't need to discuss it here. We have no information anyway. So you see there are 16 different versions of iOS 4 at the moment, and when you do the math, you can see there are probably 12 times 16 versions, but luckily it's not that case. When you look at this little picture, you see that not all of the versions are available for all of the devices. Basically, the light green stuff is all the devices we can download the firmware for, and we have the keys for the firmware, so we can decrypt them. And only for the iPad 2, there's the 4.3 version, and we don't have the keys for this three firmwares. So in total, you can see there are 81 different combinations. So when you have no idea, you just know the device is running iOS 4, one of these 81 things could be your target. So and now the question, how likely is it that something is your target? And there's statistics I got from a German IT magazine. And the audience is very technical because it's an IT magazine. And it's a visiting visitors between 1st and I think 20th or 25th of September. And you can see, which is very strange here, is that mostly they have iPod and iPhone visitors, and there are very few iPads. Maybe only the users of the site are not using iPads, or maybe iPads are just not so common in Germany. But the site owner could not explain why it's that low. So he doesn't know if it's like a glitch in the statistics, but it seems like we have a lot more iPhones and iPods than iPads. Or at least this site. So when we look at what kind of major version is used, you will see that there are very few iOS 5 beta users at the time. A little bit of users for iOS 3 and below. And the majority of 96.8% is running iOS 4. And now when we look at the minor version, we will see that the earlier iOS 4 versions are dying out, and there are still a lot of 4.2 users, most probably in Germany because of the iPhone 3G, because the iPhone 3G can only run on 4.2.1, and we have a lot of iPhone 3Gs in Germany. The majority is, however, on 4.3, which includes ASLR, and but you see that about 22% of the users are running without ASLR. And now we can break down the users a little bit more, and we can see that about half of the users are running the latest iOS 4 build, but about 48.4% are still running older versions, and so are vulnerable to this jailbreak me.3 exploit. So you can remotely jailbreak these iPhones, which is about half of the users. And of course, you see there are a lot of different versions, and a good exploit should support multiple versions. So the next thing I want to tell you about is like when you look at iOS 4, there's like different phases or different eras of exploitation because the protections changed a little bit, and you can just say there's like iOS 4 to iOS 4.2.x, and there's iOS 4.3.x, and of course iOS 5, which came out yesterday, I think, and yeah. So with each new era, you have new security features and new mitigations, and I will go through them shortly. So the basis is that you have like a non-executable stack and heap, and this is strictly enforced by the iOS kernel. And you cannot just like have memory that is executable and writable at the same time. The kernel just doesn't allow that. Additionally, the code signing ensures that code can only be executed if there's a digital signature from Apple. And therefore, all exploits must be 100% return-oriented programming. And in this times, we also did not have any kind of ASLR in iOS. The exception here is that, of course, some of these protections are not working on jailbroken iPhones, but still, at least the beginning of an exploit for a jailbroken iPhone must still use a little bit of ROP to actually like map the memory writable and executable. Yeah. Another thing you need to know is that on iOS 3 and above, you have no libraries on the device anymore. Everything was moved into the shared cache, and this is usually mapped at this, it's always mapped at this address. And the cache looks like this. You have like 3 mappings inside the cache and the code signature. And when you look into the cache, you will see that the first part contains the text segments of all the libraries. The second part contains the data segments of all the libraries. And in the last part, you see some other segments like the Unicode string in some library or in some framework, and link edit information. Another thing you have to know is that when Apple packs the firmware, they generate this cache, and the cache generation is done randomly. So it will pick up all the libraries and just pick them randomly and then load them after each other. Which means then that when you have like when you have like different devices, like the iPhone 4, the iPod 4, and so on, they all get their own firmware, and every time the firmware is generated, the load order is different. So for all of the devices, you have the libraries. They may be the same binary file, but they are loaded, they're mapped to a different address. So this means we had like 81 different devices and versions. So there are 81 different load addresses for all the, without ASLR, 81 different load addresses across all the devices for the same library. And when you look into the cache, you see also there's the modification time and the inode inside. And you see there are the same inode and the same modification time. So most probably they're always the same binary. So now let's go to the newer versions, to 4.3. And now Apple added something called the just-in-time compiler, the Nitro compiler to mobile Safari. And this adds something called dynamic code signing, which allows Safari to actually have writable and executable memory. Of course, this weakens the protections a bit, and I will not go into it at all because Charlie Miller will have a whole talk about it in next month in Taipei. So I will only care about the ASLR for this talk. So this ASLR in 4.3 basically randomized the dynamic linker, the dynamic shared cache, and the main binary. When you look at the main binary, however, you will see that when you compile an application for a new device, for a new with a new SDK, you will see that the Xcode will compile it as a position-independent Mach-O file. When you compile against an old SDK, for example, to have compatibility to older devices, then Xcode does not generate a position-independent file. This means that all the applications that are running, that are also running on old devices like Twitter, like Facebook, they all want to be compatible with all the old devices. They're all run without, they are all not position-independent executables. So in all these cases, the main binary is not randomized. Actually, I think in the wild on my iPhone, I have the only applications that are randomized are these from Apple. Every third-party application is not randomized in my device. So when we look at the dynamic linker, it was always a binary with location information, so it would be possible to move it around all the time, even in old versions. But the kernel didn't do that. Nowadays, the kernel will randomize on start of an executable. However, the dynamic linkers only slide it if the main executable is slided, and only by the same amount. So if the main executable is moved by 4 kilobytes, then the dynamic linker is also moved by 4 kilobytes. So for most of the application, for the third-party application at the moment, there's no shifting of the dynamic linker. And when you look into the shifting, you will see that the shifting is, well, the random number generator is good, but it only has 256 possible outcomes. So there are only 256 different positions the main binary or the dynamic linker can be moved to if they are actually moved. The shared cache, on the other hand, is like one big blob, and because of the code signing, Apple cannot just like shift all the libraries around, shuffle them. They can only shift the whole block of libraries by a certain amount. So the whole block moves left or right or up and down in memory. Therefore, all the libraries, if you know like one address inside the library, then you know all the other addresses, because they are all at the same delta. Yeah, this is all done by a new syscall. In my last Hack in the Box presentation in Amsterdam, I explained a little bit better how it works, but we don't need it here. But the thing is that there are only about 4,200 different base addresses even for the big cache. So in summary, this means the dynamic linker and main binary are only in like 556 different positions if they are moved at all. Before that there were like 48 different load addresses for the for the cache. Before there were like 48 different load addresses. I think there's something wrong on the slide. Anyway, now you have like 48 times 2,000 possible load addresses. Oh yeah, no. Okay, the number 48 is, of course, all the old firmwares that don't have RSLR, so there are only 48 different firmwares that have the capability to have RSLR. So there are, for this firmware, so you don't have like 48 different load addresses for a library, but in this case, because of ASLR, you have 48 times 4,200 different load addresses. So this means the odds to hit the right gadget is like 1 in 200,000. So this means we will always, especially for old apps, we will go to after the dynamic linker or the main binary because they're not moved. And for new apps, it seems to even be, to still be better to go after the dynamic linker, because it's only 256 instead of like 200,000 different possibilities. Well, 4,300. So in iOS 5, which was released yesterday, So therefore there I don't have any full analysis. I only saw some crash dumps. And in this crash dumps it looks like now the dynamic linker is always moved, even if the main binary is not moved. So in this case maybe you want to go after the main binary. Okay, this was the introduction. So now the question is, we have yet certain odds, like we can hit the, we have 81 different targets, and with RSLR we have like 256 different positions for the dynamic linker, and 4,200 for the cache. So can we improve our odds? And the first thing, we cheat our odds by we attack the dynamic linker. Again, to find a specific gadget inside the cache is 1 in 200,000. And therefore the dynamic linker is the weakest spot, and we will do some more analysis. So you remember this picture. These were all the firmware versions that are available for the iPhone or and the other iDevices. Now we want to know what dynamic linkers are these firmwares running. So this is like the most colorful slide I ever had in any presentation. This is, you can see there are actually 13 different dynamic linker binaries across all the iDevices. You see here for the 4.3 tree, you have always one dynamic linker for 2 versions. And in the older days, you had one per version, about one per version. And you have a different dynamic linker between the ARM6 devices and the ARM7 devices. Yeah, well, of course. And for the iPhone 4 CDMA version, you also have different dynamic linker binaries. In total, there are 13. So now you can split that up in, on the one hand, you have 10 dynamic linkers for the firmwares without ASLR. And you have 3 different dynamic linker binaries for the other case, for the ASLR case. So basically you have 3 times 256 possible addresses for the dynamic linker, for gadgets in the linker. And instead of 48 times 4,200 possible addresses for the gadget in the cache. So you see it's a lot better. Basically, when you calculate the numbers, you see either 1 in 200,000 or 1 in 778 for a new application, or for an old application, you only have like 1 in 13. So that's like without any trickery. So the question is, can we get any better than that? And that's why the whole talk is about so-called ropes that work in multiple environments, so-called multi-environment ROP payloads. And the idea is very simple. When you look at this ROP payload, and I ask you what does it do, then you cannot answer this question because you don't know what is the target environment, so you don't know where the libraries are. You actually don't know what's hiding behind all the addresses. And that's why you cannot tell me what it will do. And you can even not tell me if it's like a full payload or if it's just like a small snippet of a payload. So in order to interpret what it's the meaning, you have to put it in a target environment. So the first environment I want to put it into is like the iPad 2 CDMA, the latest iOS 4.3 version. And when you go to the gadget, you see in gray, this is the program counter right now. And then you disassemble the ARM opcodes. You will see that there's it tries to write a byte from the R5 register into some address that is at the R6 registers plus 11. Of course, this is like an exploit. So we most probably don't know the status of the R6 register at the moment. That's why it's with question mark in the register window. So when we execute this, it's very likely that this will crash. Because R6 is something, it's uninitialized. Well, basically the application that we are exploiting will initialize it to something, but maybe it's 0. So it's an illegal pointer, so it will crash. So obviously this ROP payload will do nothing else than crash on the iPad to CDMA. Now, take one of the other iPad 2 versions, like this GSM version. Again, you can disassemble it, and you will see that this time it will jump into the into 0 bytes of a Mach-O file header, of an executable file header. So there will be a lot of 0 bytes. You see, IDA is disassembling this as move R0 to R0, which is basically like a flag changing knob opcode. So it's actually only changing the flags, but not doing anything else. And of course, this is a legal opcode, and what will happen is it will execute it, and this will move R0 to R0, and will just increase the program counter, and nothing else will happen. And because R0 was unknown, so it's still unknown, and it's going further and further until we hit this one, and this is the last of the 0 bytes, and suddenly we start to go to the first byte of the real Mach-O image. So this is the real code in the beginning of the Mach-O. So it's a load of some Objective-C structure, and it loads it into the R3 register. And you can see when it's executed, it's filled. Basically, it's the delta to there. Now we add the program counter to it, so now it's a real pointer. You see we have a pointer in R3, which is obviously a legal pointer because it was created by adding something to the current program counter. So when we try to load a value from there, it will actually load. So now we have this 18 in the R3 register, and this is basically an offset inside the object for another, for the variable. In this case, I think it was from the game kit, and it's loading the number of friends. It's trying to load the number of friends you have. Okay, but in this case, the problem is now it tries to load the friends from the R0 register, but again, this is like unknown to us, so we cannot find out how many friends we have because we have no real pointer there, and again, this will crash. Okay, so let's try another device. Finally, we come to the iPad 2 Wi-Fi, and this time this looks like something usable, because this time we just end up on a pop opcode, which will pop the R4, R5, and the program counter from the stack. Well, we can just do that, and now we have filled R4 and R5, and we're in a different program counter, and our stack pointer has moved, and we are in another gadget, which obviously moves R4 to R3 and then jumps somewhere else. Well, we just do that. Again, we end in a legal gadget, and again we pop R4 and R5. We can do that. And this time we end in a gadget that moves the stack pointer into R2 and then jumps somewhere else. We do that, which will jump to another jump. We do that, and this one will move the R2, which was the stack pointer, into R0, and return from the function call. Well, pop the stack again, and now we have the stack pointer inside R0 and can write it to any arbitrary memory address. In this case, it's 41414141, which will obviously crash, but this is like just because I wanted it to crash. So we can see that obviously the ROP payload I showed you was meant for exactly this device. And what it does is it will just fill the R0 register with the stack pointer, so you can find out in your payload where you are at the moment. So what we learned is, normally when you have a ROP payload, it is designed for one environment and for one environment only. And if you try it in different environments, it will end in a crash most likely. But what can happen exactly is that you either have at the same address have an illegal gadget, like a crash or an endless loop. You can have there a different or compatible valid gadget, or you can have like even an identical gadget, like the same gadget is at the same address in another environment. So for the illegal gadgets, of course when it's crashing it's not usable because in this case our exploit will fail. If it's an endless loop, it's still not really usable for us, but it will not crash because it will run in an endless loop. So we can survive this attempt to exploit, but we cannot actually exploit in this case. Identical gadget, on the other hand, when you have enough different environments, it's very likely that you actually find some identical gadgets, but it's only happening for very trivial gadgets normally, and it's very unlikely for only a few comparison partners. The more interesting thing is that you find some gadgets that are similar to each other and do something that's not harmful so they don't crash, and they load the program counter from the stack and just return or jump to it. And the funny thing here is when you find two gadgets in two different environments and they both load the program counter from the stack, but they load it from different areas of the stack, then you can distinguish between both. In this case, I found a gadget that retrieves the program counter from the stack position 28, and in the other case from the position 4. So when you jump to this one address that has these two gadgets, you know when it takes the next program counter from position 28, then it was the first case. Otherwise, it will take the program counter from the 4th position. So you can distinguish between two environments. Now what you want to do is you want to have a way to do this for many environments at the same time and get the best possible result. And if you do that by hand, you will go nuts after a while because you have to backtrack very often. So I tried that with a dynamic linker, and after like half a day after I found some solution that was nice, I thought like, well, let's automate that. So I wrote a little ARM emulator, which I call the baby ARM, because it's really a very, very basic ARM emulator. This means it only emulates like a few instructions, mostly only the thumb instructions. And although it only emulates a very few instructions, it's good enough to find gadgets because I implement the opcodes that are used in the end of functions usually, or around the subroutine calls. So the idea is that we give it an initial state of the registers and then let it run. And at the end, either it errors out because there was a crash, or it will give us a gadget and give us a final state. And then we can check in the final state if it's like a special gadget that we searched for or not. And it's all implemented in Python, and I will release it, well, I have to clean it up a little bit, so I will release it in the next 2 days or so at GitHub. So, yeah. So how does it work? I hope you can read that. Basically what it does, first it reads in the instruction bytes from the dynamic linker binary, for example. Then it sets the program counter to 0, and then it loops through all the bytes. And basically every position dividable by 4 will be sent to the ARM emulator, and every dividable by 2 will be sent to the thumb emulator. And of course we'll just loop through it, and yeah, in the end it will give out all the gadgets that were found. When we look at the inner loop, we will see the first thing it will get the initial state, because the initial state tells it, like, for example, all registers are unknown, or we have a stack pointer in register 0, or we have the value 15 in register 4. If we know this about our crash, we can just put it into the initial state, and then it will find different gadgets depending on the state. So now the inner loop will read the next instruction bytes at the program counter, and then from the state it knows if it's correct right now in the thumb mode or in the ARM mode. If it's in the ARM mode, it will give it to the ARM emulator. If it's in the thumb mode, it will check if it's a 16-bit or a 32-bit instruction, and then give it to the two different emulators. And each emulator just emulates one single instruction, and then returns. And it can return an error. This means, for example, it's a crash or it's an opcode we don't support. So it's an error and it's no gadget found. The inner loop ends. If it's not returning an error, then we check if it's in a desired state. And desired state could be, for example, we have suddenly a value in the program counter that was taken from the stack. So this is usually the end of a gadget, because it's a pop or a jump to some program counter, to a new program counter. So if we are not in the desired end state, we just adjust the program counter for the next run, which is usually just +2 or +4, but sometimes it's like in a branch instruction, it's something different. But if we are in this desired state, we collect this gadget and output it to our main loop. So what's all inside the state? The state contains, of course, all the registers. It contains all the flags, the IT block information. If you know ARM, then you know the sum, then you know what the IT is. It contains the CPU mode, so if it's run in ARM or thumb mode right now. And it has the system state, like there's an error condition or there's a stop condition because a desired state was reached. When we look at the flags, we emulate all the flags like negative, carry, overflow, and 0. And the flags can be either in the state unknown, which means we don't know if the flag is set or not, or it's in the state value, which means we know it's set or not, and then in this case it can be set or not. For registers, it's a little bit more complicated. We have far more states. We have the unknown stage, which means we don't know the value of the register. For example, right after the exploit is happening, we actually know the value of a register. We know the value was popped from the stack. It's a stack value. And so it's a user-defined because we can define it in a ROP payload. Or it's a stack pointer value, which means yeah, basically it's a stack pointer. It's a copy of the stack pointer. Yeah, and in the beginning I wanted to add some other things like a normal pointer for memory access and a program counter value, but it turned out I don't even need that for my stuff. It will maybe improve the analysis if I do that, but right now it still works without it. And depending on what state the register is in, the value means something different. Of course, for an unknown value, it's just nothing, it's just ignored. For a value state, it means it's the actual value. For a stack value, it tells you what position this value was popped up from the stack. So it's a stack pointer. For example, at position 8, register 3 was popped. This is the information in there. And of course, the stack pointer value types just is the value of the actual stack pointer. I start by 0, so it's not a real stack pointer, it's just starting at 0. So when I said on Twitter that I implemented an ARM emulator, everyone was like, yeah, why don't you base it on something else, and why don't you base it on IDER or something like BinNavi? And one of the reasons why I wrote my own stuff is, when you look at the other tools, they usually, when they look at a disassembly, they can only disassemble something as either in ARM mode or in thumb mode, and they cannot jump into a 32-bit ARM instruction or into a 32-bit thumb instruction. So a lot of things they will miss. And one thing they will miss is that like nearly all of the ARM mode function epilogues are actually at the same time function epilogues for thumb mode. You can see in the first case there's like the ARM mode, it's loading some registers from the stack pointer, from the address of the stack pointer, including the program counter in the end, so it's returning from a function. And when you just disassemble the same bytes as thumb, you will see it's shifting around the R0 register and then pops some registers, including the program counter. So it's also return of a function. And all these things will be missed if you use something like IDER or BinNavi as base. So now I can use my baby ARM for finding gadgets. And of course, Normally I say, okay, it's a crash in a binary, it's an overflow, so I don't know about any register, everything is unknown. So by definition, the only gadgets it can find are gadgets that pop the program counter from the stack. And this is just like a collection of some gadgets it found. Of course, it found far more gadgets in the dynamic linker, but you see there's some that just pops. Sometimes there's like an end before, there's a move before, or there's a branch before that. So, and you can always see at what address the program counter was taken from the stack. Yeah, this is just like a basic example how to use it. But if you want to apply additional restrictions, you can just check them after it returns all gadget found. You can just check the end state. So what you can do is, for example, you just first initialize it's a completely unknown state, and then set the register value of R4 to some value, and then you let it find all the gadgets. And in the end, you will check which of the gadgets suddenly has the same value in R0 as R4, and then output all the gadgets, and you will see these gadgets always all move the value of R4 into the R0 register. So sometimes it's done directly, sometimes you first have a branch, sometimes it's moving it into the R6 register first and then moving the R6 register into the R0 register. So it's all like these kind of gadgets. The next thing that you may want to try is you also want to find all the other so-called free branch instructions. So you want to find something like BLX and some register, because it's also usable for ROP. Well, you shouldn't call it ROP then, but it's code reuse. So how you do that? First you go through all registers and give it a stack value, which means the emulator believes that each register is under your control, so a BLX R3 will suddenly be valid. What you can do now is you just let it generate all the gadgets, and in the end you check if one of the registers contains a register of type SP value, which means somehow inside the gadget the stack pointer was moved into one register. You can see it finds different kind of gadgets. On the left side, all the gadgets move the stack pointer into R2. The stack pointer is in R13. And on the right side, the stack pointer is moved in the R0 register. Okay, so that's how it looks like, the output, and how it will be working. So now the question is, how can we use that to improve our odds? So when we remember, I told you there are 13 different dynamic linker binaries. And what I did is I downloaded all the firmwares and extracted all the dynamic linker binaries, and just renamed them to dild underscore and the MD5 hash of the binary. And then you can get this table of things, and all my tools now work on this table of things. And what we can do now is we can use our baby ARM, use it in a Python script. And what we do is we load all the text segments of all the binaries into memory. And then for each text segment, we let baby ARM find all the gadgets it finds for each position in the text segment. And then we intersect the results. And we will find, well, if we are lucky, we will find addresses where it finds for different dild binaries, it finds basically the same, a gadget. It finds a gadget for the same address. Or what I didn't tell before is, I split that in two groups, before 4.2.1 and after. For one simple reason, if I did this experiment before, so I know that it's not possible to find something that will work on everything. So this is the minimal set. For half of the things, I can find common gadgets for the first half and then for the second half. I will only demonstrate it for the second half now. So when you actually ask baby ARM to find something, you will see it finds in each of the 7 binaries, it finds a gadget at the specific 2FE015E8 address. And you can also see that it's what kind of gadget is found. First something complicated, and in the end just like a POP R7 and PC. And you can also see in red what the address of the program counter on the stack is. So you see first this first gadget, if you use it, will allow you to distinguish between the ARM version ARM6 4.2.1 and all the others, because the ARM6 one will load the program counter from position 32, and all the others will also have like a valid gadget there, and they will load the program counter from the position +4, because it's the R7 PC gadget. So obviously the next step is we will try to give baby ARM the other 6, the remaining 6, and try to find some gadget that is common among all of them. And when we do that, we will see that this time it clustered in 2 different gadgets. They're very similar. It's both times a branch followed by some pop. And basically, it's using the first gadget as start point. So when you count now, the program counter is taken from position 20, which is actually 16 plus the 4 from the last time, because this gadget starts at position 4. And the other gadget starts at position 4 also, but it takes the program counter from this position 24. So now by using 2 gadgets, we obviously can distinguish between the first one, the ARM6 one, and we can distinguish between these 2 groups. Obviously the next step is we will try to go further at a 3rd gadget. So again, we ask for both of the groups, we ask, but this time independently. For both of the groups, we start baby ARM again on the 3 binaries. And in the first case, for the old dynamic linkers, it will return 2 groups again. One spans the first 2 dynamic linkers, and the second group is the last one. And yeah, you see again, this is a branch and 2 pops, and the other one is just a pop, and it's loading the program counter from different offsets again, so it's usable. Basically, I had to try a little bit around so that they don't collide, but yeah. Because I get a list from baby ARM of all the gadgets, and I just take one that don't collide. And for the newer dynamic linkers, you have the same situation. The first 2 are found as the same gadget, and in the second case, for the last one, there's a second case. And again, it's like either a simple pop or a shift and 2 pops. And obviously now we can distinguish between the first one, the first group, this one, and this one. So we have 5 different groups right now that we can distinguish between. And what we would do now would be, of course, well, try to split up the other 2. And you can try that, or I tried that, and then I realized it cannot find a way to distinguish between both of them. And the reason for that is, when you look at the first 2 dynamic linkers, there are only 89 different bytes in there. So they're basically the same binary, just some field is different. Maybe some checksum is different or something like that, or some version number is just different. But aside from that, they are byte identical. And in the second case, there are even only 66 bytes different. So, yeah. So this means for all further exploitation, they are basically the same binary for us. So all the other gadgets will be in the same place, with maybe like a very, very few exceptions that fit into these 66 bytes. but I think the difference were in the header, not in the actual text segment. So basically the text segment should be more or less identical. So now we have collected all these values, and now we can like just put them into our ROP payloads. And well, I just see I missed one slide that showed it. So so basically what we have now is we have one ROP payload, and in the beginning we put the first distinguishing gadget, then at the right position the next one, and so on. The position where we have to put it we know from the red numbers, and then we can build it. And this would be then what I call the switcher payload. And our whole payload in the end will look like this. We have the switcher payload and some copy stubs, some real payload, and then the shared payload data. And the switcher payload, we just use, it can distinguish between all the binaries. And now we need stack advancing gadgets because in the first group, in the switcher payload, now we have the problem. At some point we know, okay, this is exactly this binary. But what is the next gadget we jump to? We somehow want to come from the switcher to the copy stub 1 in the first case. We want to come from the switcher payload to the copy stub 2 in the second case, and so on. So we need stack advancing gadgets. So we just return to a gadget that will move the stack pointer around so that we end up in the right copy stub. And when we ask baby ARM to find something like this, we will find, for example, these gadgets that move the stack pointer by 48, 32, and 44 bytes. And this is actually good enough because our copy stub will be very, very small. Our copy stub will be 40 bytes. So this is a copy stub. So for each dynamic linker, for each of the in the group of each of the 5, we need to create some gadgets that will implement this pseudocode. And this pseudocode tries to retrieve the current stack pointer, then copies the data from the current stack pointer to some known location. For example, we just take the BSS segment of the dynamic linker, just some writable location that we know. Then we set the stack pointer, the new one, into the known location plus some delta. The delta will be calculated from the address of the copy stub to the payload we want to jump to. And then we just like return there. And this sounds very complicated, but in reality, you can just do this with these 10 stack values, and 2 of them are even unused. The gray ones are unused. The yellow ones are the data, like the known location, the size of the copy operation, and all the other things are like addresses of gadgets and functions. So these are 40 bytes. So for every dynamic linker, we can generate these 40 bytes. We have just to take the different address of the gadgets, and for the older linkers we need a little bit different gadgets. For the first 3 cases we can just like take the different addresses, search the same gadget, just put in another address, and then we have like 5 blocks of 40 bytes, and then we have all our copy stub. And at this point we can generate the actual payload, and this can be some longer ROP thing. It can be like a real kernel exploit that will completely jailbreak the device, but in this case we have to do it 5 times with 5 different gadgets. It can be simply vibrate shellcode, which will be very unusable for an iPad. But yeah, for iPhone it will vibrate no matter what iPhone you have. You can steal a file, of course, but my favorite is that you just implement some connect back. that will post information about the current environment to the remote server, and then the remote server knows exactly what version you are on, and then it can give you back a payload that is only designed for your specific cache. I say cache in this case because in the cache, of course, you have 103 megabytes of data, and there are far more different gadgets you can use than in the dynamic linker that is like only less than 20 pages long. No, less than 30, I think less than 30 pages long. The dynamic linker is less than 30 pages in comparison to like 103 megabytes of gadgets that you can use. Yeah, so the pseudocode of the connect back payload will look like this. You first create a socket, connect to the socket, then of course it's not that simple. You have to check that the write succeeds and writes everything. So you write all the image information which contains the slide of the dynamic cache. Then you send the first 256 bytes of the cache, which should be enough to identify what cache is actually running on the other side. Then you read the size of the new payload. You read the payload at the no location 2, set the stack pointer there, and then you return there. Actually, I will after the conference. I don't know if this week or on the weekend, I will release the actual working payload that does implement this one for all the dynamic linkers. So, and the last thing in my payload would maybe be shared data. When you have like strings or so in your payload, you will just put it all down there in the shared data, because all the payloads they will just use the same string, so you can just address it. Because once you executing payload 1, 2, 3, and 4, and 5, you are in a known location, so you can make the ROP payload a little bit easier, because you know where what data element is on the stack exactly, and then you can address it directly. You can change the parameters of the next function call by writing to the next parameter, because you know exactly the address. So this is a lot easier. And so you can always reference the shared payload data. Okay, then there's one more thing. Haha. What about ASLR? So when it comes to ASLR, we will just concentrate on one binary. We just take the latest dynamic linker for the 3.5, and we again tell baby ARM to find all the gadgets, which will be the same as before, but this time we collect the gadgets by memory page offset. So we just take the lowest 12 bit of the address and collect them in buckets for the lowest 12 bits. And so we find gadgets that are in the same page offset, but on different pages. You can see it found 4 in this case on the left side and 4 on the right side. The differences on the left side, basically it takes the program counter from 3 different addresses, and here it takes it from 4 different. So this is a better case. And what does this mean now? When you jump to a page, well, it's actually here. When you jump to a gadget inside the dynamic linker, you have a 1 in 256 chance to actually hit the gadget that you wanted to hit. But by returning to this red address here in the lower right corner, when you return to this address, then because it's at the same page offset, there are 3 times, well, in total there are 4 times. 4 times at this page address there is a valid gadget. So suddenly your chance to hit a valid gadget is 4 in 256, which is 1 in 64. So you have a better chance to actually hit the a valid gadget than before, which is still not a lot, but when you have like a mass attack, and suddenly you can attack, with the same exploit, you can suddenly attack 4 times more people. That's quite convenient. And now the actual program counter, which one of them is used to determine the ASLR slide. So in this table above, you can see if the very first program counter was taken, then obviously the slide of the dynamic linker is 1A and 3 zeros. If the second one was taken, the slide will be 1, 4, and so on. And so you know exactly the off that your dynamic linker was moved. And so again, you can just like calculate for each gadget the moved address, and then you do the same as before, but this time you just do it for 4 cases. It's better than nothing, but not what I hoped for. Maybe by implementing more opcodes and also some opcodes that help you to support a whole function call, inline function call, maybe you can get increase the chance. So when you try the same thing for the shared cache, which is like 103 megabytes of data, and only shifted by 17 megabytes. So you have a moving window of 17 megabytes that you have to check. And I created these gadgets for the moving window. And you can see on the left side, these are the number of gadget collisions it finds. You see in the beginning it's like a medium good, in the middle there are very few gadgets that are colliding, and in the end it's getting better and better and better. Which is just a position inside the file. This is just random. Oh, this is for the iPhone 4. So basically when you do the same thing for the iPad 2, it will be different. We'll see it look different. But the problem is, while it's 119, which would be very nice, like 4,200 by 119 is a far better chance than for the dynamic linker. But the problem here is that when you look at the different program counter locations that are taken, in the very best cases, only 30 of these 119 are different program counters. So to just survive the first gadget, the chance is 2.8%. But because you only have like 13 different program counter locations, but 119 different collisions, you have many gadget clusters you have to distinguish between. So your actual shell code will be longer and longer and longer and longer, and creating this by hand will be like completely stupid. And in the end, when you look at the numbers, the work you put in there to construct this payload will not be worth it, because the odds that you get are still not that good that it's it's a good idea to involve so much work. Okay, so the conclusion of all this is we have proved that multi-environment gadgets can improve our odds. In the non-ASLR case, we can create one ROP payload that can own everything above 4.2.1, no matter what device. And we can also do that for the other linkers. We can have one ROP payload that does it for 4.0 to 4.1. I didn't show that, but it's the same thing. We also can see that for the ASLR case, we can improve our odds, but the odds are still low. And doing this kind of attack for the dynamic shared cache, delta shared cache, is not really worthwhile. The disclaimer, however, here is that all the numbers are generated with the current version of this baby ARM, which is just a very limited subset of the instruction set. So maybe if I add more instructions, I can get better results. But I don't expect it to be so much better. Yeah, that was it. Any questions? No questions?
Yeah. Okay, well, thank you very much, Stefan.